Okay, let us start. So, as a summary from where we left it last time, you can see that, and you have this available to you, so I believe you can see it on all terminals, all right? We took a parallel plate structure. Now, from this point on, we will call it a parallel plate waveguide, because we are exciting with a source that varies with time. And all of these structures we're going to see from now on, they are going to propagate what we call waves. So the correct terminology from this point on will be a parallel plate waveguide. And we all know that when we looked at this structure in statics, we just called it a parallel plate capacitor. All right, because that's what happened really in statics. When your frequency goes to 0, that becomes a capacitor. But when your frequency is higher than 0, the structure to your right propagates waves. So this is a parallel plate waveguide. The same way, from this point on, we are going to call the coaxial, not a coaxial capacitor, we're going to call it a coaxial waveguide. Or sometimes, when people in the field, they will call it coaxial cable. All right? In courses like that, we call it a waveguide. That's the formal name. In the field, people will call it coaxial cable. It's the same thing. All right. So what is the characteristic of these two? They have two conductors. So now we are talking about two conductor lines. All right, and in two conductor lines or waveguides, or the characteristic is that if the frequency is low enough, if those geometries have a cross-section which is much smaller than the wavelength, so size of cross-section, each of the dimensions, so each dimension, not just a product or something, not an area, but each of the dimensions are much smaller than the wavelength. These two conductor lines create transverse electric magnetic waves. And we talked about this specifically as we looked at this particular example of the parallel plate last time. All right, so these structures now, when this applies, create TEM waves. What does that really mean? That if a structure like that, it could be a two-wire structure, right? Like this. This is another two-conductor waveguide or two-conductor line. It's another one. But let's go back to the example we had, because we don't want to deviate from that. So if we have a parallel plate waveguide like this, and this is the cross-section here. So let's assume that this is X, or X, Y, and Z inside. All right, since we are here in the beginning. So that is moving inside, so Z is like this. All right, so you have that coordinate system. Then, if each one of the dimensions, W and H, are much smaller than the wavelength, then they create a wave that has the two cross-sectional, the two fields, electric and magnetic, they are perpendicular. So, for example, the electric field is going to be coming, in this case from here, like this. The magnetic field is going to go like that. All right, that's what we saw. And then what else it happens? This wave that has only these two field components, one for the electric, one for the magnetic, and they're perpendicular, the two, propagates along this direction, Z. This is a waveguide that creates these waves, all right? So there are two conditions for these waves, both necessary. That there are two conductors involved, and parallel, of course, and the size of the cross-section, each dimension of the cross-section, is much smaller than the wavelength. When you have that, no matter how the shape looks, they may be like this. Does not matter. They may be like this. Let me think another weird one. Not that we make those, but I'm telling you, theoretically, could be like this. All right? They will be TM waveguides if these two conditions apply. So, why is that important? This is important because then we don't have to analyze each one of them every time we have something like that, even if the cross-section might be very complex. And we can directly go and make those assumptions that the electric and magnetic fields are perpendicular and they propagate along the third direction. Okay, the moment you make this assumption, then you can define a voltage and a current. That's the goal. The goal is to go from E and H, and as a matter of fact, from an E that has X, Y, and Z, and from an H that has X, and in fact, N time, and an H that has X, Y, Z, N time, the goal is to go down to a V that has Z and time. So we simplify, we reduce the problem. Engineering is always about reduction. We never solve the most complex case, all right? If you cannot reduce, you're not a good engineer. That's the bottom line. And there were some amazing engineers before the computers were built that they did everything because of reduction. So that's what this is what it has to be here, all right? If there is nothing else, you will remember that is the most important one. And then this one to an IZT, first level of reduction. So instead of 4, 2 parameters. One more is because we assume harmonic excitation. All right? Which means that your source is going to be this or that. The two are identical. They only have a difference in phase. So what does that mean? That from here we are going from the time domain to the phasor domain. One more reduction. Where now we have only, instead of V of Z and T, we have only a V of Z, and then we have only an I of Z. And what do these two reductions do for us? Instead of having complex geometries like this and deal with 4-dimensional problems where we started, we have geometries like this, one-dimensional. What best can you do? There's nothing better than this. Go from 4 dimensions to 1. All right, that's the whole idea here. And people developed this theory in the early part of the 20th century. That's how far it goes. Smart people. Okay, so here you can have a load. And then here you can have your source. All of this in the phasor domain. And now we have one-dimensional problem to solve, and we can do wonders with this. All right, where we stopped, therefore, okay, here, is that we have the final solution for this final solution, right? When these two are written in this form. So now I can tell you, as we showed last time, not only I have taken this complex problem to this form, but I also know the solutions. Not quite fully, but I know enough. And then I will show you how we really go to characterize everything completely today, that is. So V here of Z, which is the phasor of the voltage along this line, because this is the Z direction. And we are going to start Z equals 0 here always, and we'll go here to negative values. So let's assume this is minus L. That's the length, L is the length of this line. And then I of Z, the other phasor, they have two possible solutions, depending, of course, on where you put your source to excite it, where you put your load, and what kind of load you have. What are the two possible solutions? Any of the two or a combination of the two, all right? And the combination will depend on these two conditions. So which are those two? V of Z can be either a V plus of Z or a V minus of Z, or any combination of these two. And the same thing with I. I can be, and I will remove the Z here, an I here of Z going this way, or an I minus of Z going this way, or any combination of the two. Now, we have seen enough, but we have not defined the solution yet. Why is that? Because I have come down to these two possible solutions, but I still do not know the coefficients. I know that beta is omega square root of epsilon mu. I know omega is 2 pi f. I know epsilon. I know mu. But I do not know V naught plus. I don't know V naught minus. I don't know I naught plus and I naught minus. So I have work to do, all right, at this point. So instead of here, now that we've gone this far, to be able to find the 4 unknown constants, because those are constants, and they will be complex constants, but they're still constants, all right? We will have to, instead of continuing from here, which can get a little complex, and to be able to squeeze a little bit the time, we are going to start from a different representation of this. And I will show you exactly what I'm talking about. So I will erase all that because I don't need this anymore. So this is the past here. We're not going to talk about those again for the rest of this class. Okay, so we understood that. We know we have harmonic fields, excitation. Okay, let us assume that this L, the distance, is 1 unit length, whatever that means. If your unit length is 1 meter, is 1 meter. If it's 1 millimeter, is 1 millimeter. All right, 1 unit length. Do you remember what we did when we looked at the parallel plate waveguide? Which circuit quantities did we calculate? Capacitance? Yes. Capacitance and resistance from statics, electrostatics. So, when we had this one, we found C, and that's capacitance per unit length. You remember why it's per unit length? Because we found it in farads per meter. And for us, the meter was the unit length then. Okay, that's how it was not a pure farads. It was farads per unit length. Now, we did not show it then like this, okay, but what we considered that we had a geometry that was long, like they had some kind of a length in there, and we found that in farads, but we always had in mind that it was for this much length of the line, all right? That meant that if the line was twice as long, it would have much higher capacitance, okay? Now, so when we found the capacitance, in reality was a capacitance for if this still was the z direction, and if that was L, we found that that was a capacitance for a given length L. And then I would have to write it like this, meaning more length, higher capacitance. So the same thing, we found a resistance. So I will say we found in reality capacitance per unit length. That's what I will call it from this on. And a resistance per unit length. Because for a given, in reality, was ohms per length, but it was a resistance per unit length, okay? Resistance per unit length, okay? And then when we did magnetostatics, we found L per unit length, which is a inductance per unit length. But in magnetostatics, we did not consider losses. So if we had losses in the conductors, obviously, when do you have a loss in a conductor? What do you need to have what is the value of the conductivity in a conductor to have losses? Less than infinity. It can be very large, but not so large that practically you have no losses. Every conductor, there is no perfect conductor. Perfect conductors exist only in our examples. A good conductor will have very large value of its conductivity, but will never be infinite large, all right? There is no infinity, for example. Yes?
What about like really cold conductors?
They will have less, but not zero, all right? Superconductors do that, less. Many orders of magnitude less than the same conductor in regular temperature, but never zero. And then that's why we said last time if sigma 0, you remember we said in the goes to infinity, so if the conductivity of a perfect conductor is infinity, the conductivity of a lossless material is 0. Remember those two? Okay. When we solved this problem, we did not assume that we have losses in the conductor. But if we had losses in the conductor, we would find another resistance from conductor losses, all right? And that would have been, of course, resistance per unit length. Now, This is what we got from statics. Let's go now to this one. If this is a unit length line, then I can claim at this point, and I can claim it correctly, that I can represent it in a also different way. And I can do it in this form. I will have, instead of this line from here to there, I will still have this point. If this point is A prime, B, and B prime, this line can be represented by this circuit. I will draw it for you, and then we'll talk about it. Okay, where this is A prime, B, and B prime. And here again, I will have this source. And then here I will have this load. Where L is this one per unit length. C is this one. Resistance, and I will show it here as a conductance, which is 1 over R. And why do I show it as a conductance? Because it's in parallel. So now I will show it as 1 over R, but in reality, I will always have, instead of R, a G. So always in circuits, you're going to see a G here. And that is practically the inverse of that resistance that we found. But we write it as a G, as a conductance, primarily because it's in a parallel combination. And that is going to be easier to have that as G. And then this one is going to be R. I can call it, instead of R prime, in fact, I can put it here, because this is how everything is represented. So inductance, resistance due to losses from the conductors, capacitance due to the two conductors, conductance because of the losses in the material. Is that, any questions about that? And as a matter of fact, we have the values for all of these. So let me see. Let me go to, no, this one. Okay, so let's go here and start this one. Okay. Let's see what that is. Oh. Okay, so that shows. So these are our lines. Two conductor, all of them, all right? We talked about TM waves in all three coordinates. This is what you see here practically, the circuit representations of the coaxial and parallel plate. This is our transmission line. We have put it in a box in there, but the rest is the same. And here is what I've been discussing with you. Delta Z is there because each one of these components has a length of delta Z. All right, I called it unit length. In this one, you can show it like that. So if the value, if this is given to you as resistance per unit length, you will have it to multiply with the length of the true line to be able to find its correct value, obviously, all right? So in this case, you have that circuit, and the values for this are given. In fact, you can have them available. So let's look at the parallel plate waveguide, which we did for this class, and try to write those the values of these circuit elements the way we found them when we did the analysis. So for C, it's epsilon W divided by H. Okay, and that's per unit length. So there is no area here. Do you understand the area? We had an area. Do you remember for the capacitor? It was practically this one, what we had calculated then. But since we are going to multiply it anyways later, we remove that. So that's per unit length, capacitance, so in farads, unit length. Okay. What did we find about the resistance? Was this with the sigma there? Sigma W over H, and it's in ohms per unit length. L, it was mu H over W, and that is in henries per unit length. And RC, which now is that R prime that you see in there, it's 2, what did it say? 2 R sub S, which we have not calculated ourselves, over W. And you know what this R sub S is? Is the surface resistance, as we call it. We have a new entity. We have not seen it yet. You will see it in 130B. But this is called surface resistance of the conductor. It's a measure of characterizing the conductor losses, all right, through this surface resistance is given. So for any given conductor, this is given a part of its specs. So you don't have to calculate it. All right, so all of this, and this is going to be in ohms per unit length. By doing that, practically you have defined this one. And by defining this one, practically which is here, you will find you can repeat circuit, all of these like the KVL and KCL in this circuit, and I'm sure you have seen those before in physics, the KVL and KCL. If you apply those two, then you're going to find these two equations in the phasor domain for V and I. So if I were to erase this for the time being, KVL and KCL, I'm not going to derive it. They're simple circuits. I hope that you will know how to derive them because it's just KVL and KCL, but you can find that. And in fact, the tildes are for phasors, all right? But we don't have those here. So it's going to be minus dV dz equals R plus J for our circuit, omega L I of Z and minus di of Z dz equal G plus J omega C V of Z. Now, unfortunately, in all of the books, there is no unique symbols for phasors. This one has the tilde up there. Our book has a line under. I mean, other books have a bold. Other books have a script. And I have decided we're not going to use all of this. We'll just know that every time you have a J in your equation, it is in phasor form. Very simple, much simpler than trying to look at the symbols, all right? So these are the equations in phasor form. All the entities are phasors. All right. If you do this, then in this case, if you go to solve it, you will still have, if I go here, for example, and I take the second derivative of that, all right? So I can take the second derivative, and then it's going to give me minus d square v of z dz squared is going to be r plus j omega c di of z dz. And then from here, I know how much this is. So I can plug in here, and what I will have is d square v of z dz squared equals 2 r plus j omega c L g plus j omega c b of z. So practically, I found one second-order differential equation for v of z, which is the same equation. We remember this one I had here. Okay. It's very interesting because now, if for a moment, let us for a moment assume that losses are not present. I will just write the equation here so you remember it. Here our equation was d squared v of z dz squared minus, plus I would say, omega epsilon mu v of z equals 0. That was the equation we had here. Remember? Okay. So if that was for lossless. So let's assume lossless here. What does that lossless mean? It means that I will cancel this. That goes to 0. And that I will cancel this. All right? And that will go to where? Did you see that? This one, infinite. That g goes to infinity because r has to go to 0. Otherwise, if that were to go to 0, it would shorten the capacitor. So no, that doesn't happen. So what happens to this one now, exactly, as your colleague said, is going to be d squared v of z dz squared minus omega squared LC b of z in fact plus on this other side, excuse me, we need to bring it to the other side, equals 0. Now, look at these two. This one here and this one are the two identical. They are the same. From comparing the two, what do I find? That in a lossless case, lossless lines, omega squared epsilon mu, which is nothing else but beta squared, all right, is equal to omega squared LC. All right? Very interesting. So practically, from L and C, or epsilon and mu here, I can find my beta. All right? You say, well, what's the big deal? Because I already knew beta. So beta here is either omega square root of epsilon mu or omega square root of LC. Now, the interesting thing is that what it makes it easier, where it makes it easier, is when we want to find the relationship between V and I, or V naught and I naught. All right? And we'll do this as following. All right. So far, so good. This is clear. Okay. So I will erase these things that I don't need them. Yeah, but I moved them to this side. It was equal that, and then I moved it on the other side. Yes. G has to go to infinity because this is a conductance. What's that? Conductance means the inverse of resistance. Zero resistance implies infinite conductance. And when it goes to infinity, that means it does not exist, all right? Now you can say, well, I add infinity, but you remember this is parallel combination. So you add infinity to a C, and it gives you C. So I did it here. It looks weird, but that's what it is. If you were to do the derivations again, you would find here that it's only a j omega c. It's not exactly a mathematical thing. All right, so I will keep these two. All right. And I will still be in a lossless case. And I will write here for the lossless case, the only thing I will do up here is to write the relationship between the original. You remember there was an original equation that said dv of z, dz was equal to j, to r, excuse me. So it was practically j omega L because I made r equal 0. I of z, you remember that? That's what we had as the first equation here, but with all the losses then. So now I have put r equals 0. Now, if I assume that my v of z, I am in an infinite long line. What does that mean, infinite long? So we don't need this anymore, all right? I will erase that too. Because the only use for this circuit is to get these relationships that I showed you. So we'll stay with this one because we are going to use this from this point on. Okay. Let's assume that our line here is infinite long. What does that mean if it's infinite long? Continuous. How much is going to be the reflection? Am I going to have a reflection on this line if it's infinite long? No. Only this wave is going to exist. Okay? These two waves cannot form. These two waves will not form because that keeps going forever and the wave will never find the load. So only these two exist, which means in an infinite long line, V of z is only the positive part of it. Do you remember what I said? These are two possible solutions. Either one of them is going to exist or any combination of the two. That's what I said. So you don't always need to have both of them. One is going to be enough for a problem if it's the right solution. But at least you need one or both or any type of combination of two. Okay, so in this case we have only one, which is V naught plus e to the minus j beta z. Okay? Now, IZ, same. IZ, I plus of Z, I naught plus e to the minus j beta Z. Okay. I don't need this anymore because I have already found the solutions. I know them. And what am I going to do here? I'm going to take these expressions for V and I will put them back here. So we'll take these expressions of V, and I will take its first derivative. Yes?
Isn't V plus e to the positive j beta z?
No.
No? Both of them are negative that way?
Yes.
Okay.
So you remember what we said? It has a minus when it goes to the positive Z. It has a plus when it goes to the negative. So so to remember it, whenever this plus, this is minus. They are never the same sign, if you want to remember it easily. Okay? All right, so take it in there, and what I find? Minus j beta. V naught plus e to the minus j beta z equal j. In fact, there was a minus here. J in front of in the question. So j minus j omega. So you have these equations on your you see the minus sign? I had missed it right there, up there. I put it here. Okay, minus j omega L I naught plus e to the minus j beta z. All right, so now what do? I simplify things. This here and this goes. This one here and this goes. And what do I get out of this? I get that V naught plus over I naught plus equals L, omega L over beta. All right? And how much is beta for this omega, with an omega in front? Remember? Omega square root of LC. So I plug in here. And what do I find? Square root of LC. If I had done exactly the same thing while I had stayed with a parallel plate waveguide, I would have found that for the parallel plate waveguide, not for any, this is in general expression. This is a general expression for any two conductor line without losses. For the parallel plate waveguide only, I would have found that this would have been square root of mu over h, over epsilon. Only for the parallel plate waveguide, not for anybody else. Okay, but here we want to stay general. This is a very important expression, and it's called, this parameter, the characteristic impedance. The characteristic impedance of the line. Very important. Why is that? Because when the line is infinite, then the ratio of your voltage over the current is this real number, Z naught. It's not complex, it's a real number. Always real, even when you have low losses. And why is that? Because, so this is lossless, okay, lossless. If I had losses, with losses therefore, so lossless here, with low losses, and why do I say low losses? Because would you ever design a transmission line with high losses? you would lose your job if you were to do that. You should never go to anybody and say, I have a transmission line, but the good news is that I have it. The bad news is they have high losses. They will ask you to go back. So with low losses, then this ratio would be what? R plus J omega L, G plus J omega C. All right? Okay, for low losses, this become, and I have in fact, yes, I made, so I will go back to this one. But in low losses, this one goes to 0, means 0 resistivity in your conductor, and 0 losses in the dielectric. All right? So that for 0 losses in the dielectric, unfortunately, that would go to 0 losses means high resistivity, all right? So I should have said the opposite before. High resistivity, which will make the conduction 0. High conductivity in the conductors that makes the resistance 0. High resistivity in the materials that makes the conduction 0. You want to have perfect conduction in the conductors. You're going to have 0 conduction in the material. All right, these two. So this is going to give you LC. Because these are so much smaller than these, and it's not exactly 0 in low losses, but R is going to be much smaller than omega L, and G will be much smaller than omega C. All right? So that will give that. So what happens is that either in lossless waveguides or in low losses, the characteristic impedance is the same. And the characteristic impedance, therefore, in any of the lines we're going to look at will be real, always. The same is not true for beta. So now I can go away from this. And I can say the following. We found that if it's lossless, like it's there, beta was omega square root of LC. That's what we found. When there are low losses, you can find the same way as we did here, that your beta will be square root of R plus J omega L, G plus J omega C. And because they are complex and because they are products of large quantities, so this is small and this is small, but the product of this with that can be large, and you may not be able to ignore it. And as a matter of fact, it's to see how it happens. If this is, I were to do it like that, it will give me Rg, very small number. The real part will be minus omega square LC, and then I will have inside 2 imaginary components, J omega RC plus J omega GL. Okay, now this is very small. You can remove that. So you only are left with this. But the imaginary components, I have the J in here, the imaginary components can be large as well. And you cannot ignore them. So what that is going to give is that this beta is going to have a real and imaginary part. And in that case, in complex systems, instead of giving beta in an imaginary part, they will tell you that the propagation constant remains beta. Sometimes people will call it the phase constant. It is in the J. But then you will have a small component that are the losses. And in this case, your waves will look as following. V plus of Z will be V naught Z e to the minus A Z e to the minus J beta Z, where A is the loss factor. And either they give it to you or you calculate it if you have enough data, if you know the geometry. Usually for what we're going to do, it's going to be given to us. And then I of Z will be I naught plus E minus AZ, E minus J beta Z. And that's for low losses. So for low loss cases, it tells you that the wave propagates along the Z direction, but it attenuates as it goes. Now, here is to see that so you know it, but all of the problems we are going to solve from this point on will assume lossless lines. And why is that? Because if you know how to solve problems for lossless lines, then you will be able to apply the same techniques for cases with low losses. Okay? And we don't have time, obviously, in the class to do both. If for those of you who will continue in circuit design with other higher level classes, you will see cases like this more often. But I just wanted to come to this one, to use primarily our equations that we are going to use will be this one, and this one. So always lossless. And we know both the characteristic impedance of the lines and the propagation constant. Okay, any questions you have so far about anything we covered? I want to see what that is. All right, so to summarize, we did all of this last time we had the lecture, and this time to practically find three things from all of this. What I want you to remember are three things. And those three are the following. That V, so from this point on, I would like you to read those things so you know how we came down to what I'm going to write and why we use these things. But what we are going to use from this point on is the following information only, that V of Z, V plus of Z, V minus of Z, or if you like, V naught plus e to the minus J beta Z, V naught minus e to the beta Z. Okay? Then I of Z equals I plus I minus I naught plus E minus J beta Z, I naught minus E to the J beta Z. And in these ones, we have this relationship, V naught plus is Z naught I want you to remember those things, all right? These are very fundamental, and then you will need to remember those to be able to take the next steps. And then also you could prove, I'm not going to do it here, but you could prove that V naught minus over I naught minus is minus Z naught because of the way we have defined it. And that beta is omega square root of LC, or omega square root of epsilon mu. Or, of course, we may use that, 2 pi over lambda. In fact, F, excuse me, I need time to do that. Yeah, or 2 pi over lambda G, not lambda guided. Any questions? These are fundamental, this. So we did all of this to come here, yes?
I've heard this theta, is that also referred to as the wave number?
Yes. And this is the, yes, the wave number, because it's directly connected to the wavelength, and because it really specifies the phase of the wave. Sometimes they call it phase constant, wave number, phase constant, wave number, or complex propagation constant, or real propagation constant. There are these three things. Now, we can take a 5-minute break, and then we're going to start solving some problems. Now we have everything we need to solve problems, all right? Yes.
Because I still don't have the grade for the individual midterm.
What's that?
I still don't have the grade for the individual midterm.
Really?
Yeah.
I will give me your, could you, let me write down your name. Okay. Let me, in fact, yeah, I will do this here. You write your name here and then say no individual grade, not the individual midterm grade. Okay, thank you.
You want my student ID number? Or
No, no, no. Just this and that. Thank you. All right, so now we'll start solving some problems. And so we'll solve a few here. We're not going to have, I decided not to have today top hat problems, so we have more time to cover stuff. Since we are stressed for time here. But having this, remembering all of this, we're going to start solving problems right now. And the first one, I will erase here, is to solve the problem where we have a load at the end of the line. All right? So from this point on, every time I give you a transmission line, I will give you both its characteristic impedance and its propagation constant, beta. They will both be given to you. You will not be asked to derive them. And from this point on, if you need to know something, is how is the values we got for the RLC circuit, and especially the ones we got for lossless, all right? The things that we covered, but nothing more than that. So at this point, I'm giving you a line that is not infinite in length. It terminates, however, at a load, Isabel. And this line has, that's how I'm going to give things to you from now on. A Z naught characteristic impedance is going to always be real. And do you by any chance know what is the prevailing value for Z naught? Yes, that is the formula. But what is the prevailing value in ohms of a characteristic impedance of a transmission line? 50 ohms. That is the norm. And why did we select 50 ohms? Because lines with 50 ohms, they have relatively larger geometry, still very small to the wavelength, so their losses are not very high. If you go to higher impedances, you will see later, you shrink the dimensions of the strip, of the microstrip, and you increase your losses. So prevailing value, 50 ohms. If I don't give to you the value of Z naught, that implies 50 ohms. If it's not 50 ohms, I will give it to you. All right? But at this point, I will say you have Z naught and beta. And we now want to solve this problem. What do we know in this problem? That V of Z, as you can see here, I need to, you know, it's not my computer that turns off. I can promise you that. It's, it has to do with this system here, which they do it for energy efficiency, I can imagine. All right, so this one, what we start and say is V of Z has both components, V plus and V minus. And I of Z has both components. Since one has them, the other has them. I plus and I minus. What is the other thing that I know? That V, in fact, we know, of course, that V plus is V naught plus e to the minus j beta Z. V minus, and I will write it here, is like this with that. Can you see that? Do you mind if I do it like that? So we don't write four equations. And I plus or minus Z will be I naught plus or minus e to minus or plus j beta Z. What else do we know? We know that V naught plus over I naught plus equals Z naught, which is equal minus of V naught minus over I naught minus. This is what we know. These are all the equations we need. The fact that we have a load at the end, what does it say? That the total V at the end of the line, which is equal 0, so the load is at z equals 0. Okay? What does that say? What does that mean? That V at z equals 0 is going to be V naught plus V naught minus. That I at z equals 0 will be I naught plus I naught minus. And what else do I know at z equals 0? The ratio of the two is what? Exactly. So V at z equals 0 divided by I at z equals 0 is Isabel. So what do I do at this point? I take these two and I plug them in here. So this I don't need to remember them, all right? That's what we said. You have to remember all of this. It's not much. Just so you can, if you don't remember those, you're going to lose a lot of time trying to solve these problems. All right, so here, that gives us what? V naught plus V naught minus over I naught plus I naught minus. Is this a bell? What else do we have here? We know that V naught plus, equals Z naught I naught plus. And we know that V naught minus equals minus Z naught I naught minus. So practically, this is Z naught I naught plus minus I naught minus I naught plus I naught minus. Or I can rewrite this that I naught plus minus I naught minus equals ZL divided by Z naught. Okay? So, if I call this, now, I stop there for a moment, and then I'm defining also a new parameter. We have not defined this before. The new parameter is the reflection coefficient. How do we define the reflection coefficient? As the ratio of the reflected voltage wave over the incident at Z. In fact, I can define it everywhere, but the reflection coefficient at the load is going to be this. I can define the reflection coefficient at every point on the line. So practically, to be more accurate, I say I don't need necessarily to define it only at the load. So I call this ratio gamma of Z. And at the load, I always indicate that as gamma sub L, okay? So, what do we learn from here? We have found this relationship And we know that. From here, also, I can rewrite this as V naught minus divided by V naught plus equals gamma sub z e to the minus 2j 2 beta z. This is an important relationship. What also do I have? Let me just erase this momentarily and I will write it so I can write below it. I will write it a little further down. What else do we have here? That this, according to that, is nothing else but gamma L. Do you agree with that? If I go here and I put z equals 0 at the load, if I put 0 and be in the load, then I will have at z equals 0, which is the load, I will have that gamma L is going to be V minus at 0 over V plus at 0. How much is that? This. Do you agree? If I put z equals 0, the ratio of these two is going to give me V naught plus minus over V naught plus. So I have that gamma L is the ratio of these two entities. And also, as I said, I know that Z naught ZL divided by Z naught, rather. Okay, from here. It was I0 plus minus I0 minus and I0 plus plus I0 minus. I also could find out that I could have replaced this with a V's. And I could have written that as V naught. I could have done this in terms of V naught. But here is this equation. So to summarize, and I don't want to do all of the derivations here, if you use this information, what you're going to find is another relationship that it's simple and you will need to remember. So you don't derive every time. Don't try to find the derivations. From all of these, what we have at the end is that gamma L is nothing else but ZL minus Z naught over ZL plus Z naught at the load. And that is called the reflection coefficient. What happens when ZL equals to Z naught?
It's 0.
0. What does that mean? If reflection coefficient is 0, that means what? If this is 0, that means there is no reflection. All right? From this relationship, if ZL equals Z naught, the line, therefore, is matched, we call matched line. That implies that gamma L is 0, which implies that V naught minus is 0, which implies that V minus of Z is 0. No reflection, no reflected wave. Okay. Also, something else that you will see, a lot of times we will normalize the load. And we call that the normalized load. When you normalize the load, usually I show it on the board because it's difficult to differentiate between capital Z and lower Z. All right, in the notes, many books has it as a lower Z, the normalized load. I will have it with a bar over it because it's going to be difficult for me to show you the lower and the high and the capital. So a normalized load is this one. Why is that beneficial? As you will see, a lot of the formulas will become very simple. This one, for example, gamma L, will be ZL normalized minus 1 divided by ZL normalized plus 1. And a matched condition, matched line, means Z sub L is 1. Which is nothing else than this one, obviously, all right? All of this, you will see it here. So you will have it in your notes. Then, any questions? Then the book gives different, but I will do them here. They give the book here, and I would like you to feel comfortable with this, so we are going to do a few, and then I would like you to do the rest. So we'll start playing with very, very fundamental loads, like a short and an open, a capacitive or an inductive, all right? So let's try to see what happens when these 3, 4 different loads are at the end. These are fundamental loads, as we call them. So today I'll give you a homework, and you will bring it next Wednesday. Next Wednesday, since it's going to be a week. Next Wednesday, I will leave you only a group homework. So I'm going to explain as I'm erasing. And why would I give you next Wednesday only a group homework? So you will have an opportunity to come together with your groups, solve the homework, and then also decide and discuss on how you are going to work during the final. Very important to have those discussions ahead of time, not to argue during the final on how you're going to come together as a group to solve it. All right? And then you all leave disappointed. So, all right. Now you tell me. I'm going to write, and you're going to tell me, and I'm going to write. But I will draw, first of all, the transmission line. So this is your transmission line. Here. And I still have the same. We have not talked about this yet. At some point later, next time, we are going to talk about what happens here on this end. But we are talking about what happens here on this end. ZL. Z naught beta. And this is whatever distance we want to give it, L, say. L. Okay. We found, and I'm going to write here, when ZL equals Z naught, gamma L is 0. And of course, gamma everywhere is 0. And that means that V of Z has only a positive an incident, as we call it, an incident wave. How about when ZL is 0? What happens to gamma? Let me write it. I write it here because I'm here, down here. How much is that? ZL minus Z naught, ZL plus Z naught. What happens when ZL becomes 0? Minus 1. Need to remember that. So gamma L is minus 1. Always gives what? A short. All right? That's a short circuit. So short circuit. Which means that gamma Z, according to what we found, is going to be minus 1 e to the minus j 2 beta Z. Okay, we found that formula. And what does this mean? That V of Z, of course, has two components, all right? Because it's an open, the wave goes there, sees an open, which is a large resistance, very large, and then it's reflected, so this is going to have two components. Okay. Let's now see what is going to happen when this is an I said 0, it's short, all right now. ZL is open, very large. Open circuit. Gamma L, remember, how much is it going to be? Gamma L is ZL minus Z naught, ZL plus Z naught. If ZL is infinite large, what is this going to be? 1. So this is 1. Therefore, gamma Z will be 1 e to the minus j 2 beta Z. And again, V of Z will have two components. All right, let's go further down. Let's assume that Z sub L is a, what do they have there? Okay. Let's assume that it has an inductive load. What does that mean? This is going to be J omega L load. Okay? We are in phasor form. That's why an inductance becomes J omega L. Do you remember that? Okay. So then, how much is gamma L? Let us write it. J omega, bless you, as they say, L minus Z naught, J omega L plus Z naught. What is interesting about this? Can you tell me something characteristic, something interesting about gamma sub L? Yes. And then what more? Do you agree? So, the magnitude of gamma sub L when you have an inductive load is 1. You're going to also find the same if you have a capacitive load. All right? So, if Z sub L is capacitive, it's going to be minus J omega C. You agree? And then gamma L will be minus J 1 over omega C minus Z naught minus J 1 over omega C plus Z naught, and gamma sub L is 1 magnitude. So what is that I'm learning from here? An open is a bad deal when it comes to matching the line. An open is going to give you maximum reflection with a phase, an open, without phase. A short is going to give you a maximum reflection with phase. All right, if this is 1, that has 180, but still 1 magnitude. A reactive load may give you gamma L with a different phase, but the magnitude is going to be 1. So you will never be able to match a transmission line with a load that does not have a real resistor in there, and a resistor that is close enough somehow to 50. Now, it does not have to be 50, you will see, but combining, of course, if it has reactive components. But the only perfect match, it happens if only your load is 50 ohms. The only perfect match. Anything else in your load is not good, which means you will have to do something to put something in front of the load to be able to change the reflection coefficient at that point. So in other words, if I don't like the load because it creates a reflection, I can add here something else. And I can add here something else so that the combination of the two becomes what? Exactly. That one here, we are going to call it a matching network. And you do matching with different kinds of techniques. So let's see. Any questions so far? All right, an example. Somebody give you here, this example here has a 100 ohm transmission line that is connected to a load consisting of a 50 ohm resistor in series with a 10 picofarad capacitor. Find the reflection coefficient at the load for a 100 megahertz signal. Okay, so they give you the frequency. So let's try to do that. Think about it because I would like somebody to help me solve it. Now you have the solution up there, but I don't want you to look at the solution and tell me the solution. All right, the way it's written. First of all, the question I have for you is, what do you need to know before you even start thinking about the solution of the problem? Z naught, all right, you remember that we said? Always Z naught. We have Z naught. Of course, it's given, 100 ohms. What else do you need to know? ZL, which is 50 ohms. And plus J minus J in that case, 1 over omega C, okay? So what else do I need to know? Frequency, which we have. So omega is 2 pi f. So I need to find omega C. And then from there, I have this load. Okay. So what frequency is 100 megahertz? Do you remember what I told you that 1 gigahertz, I always remember that as my point, is 30 centimeters. in free space. 100 megahertz is going to be what? 300 centimeters. 10 gigahertz, 3. Okay, just that to keep in mind. But here, they give you f, so this is going to be 2 pi f, which is 100 megahertz f, c. So you compute that. And by computing this, you have z sub L. And then how do you find the reflection? Gamma L is what? Remember that? Reflection coefficient. And then, because your load is complex, this is going to have a magnitude and a phase at the load. If I know that, and if I know that the length of the line, so I'm adding now, okay? The length of this line, I want to make it, let me see, 15 centimeters. That's the length of my line. So I would like then for you to find me the reflection coefficient at this point. At z equals minus 15 centimeters. Because you remember z goes this way, and the values go negative here. How we're going to do that? Do you remember the formula for gamma of z? How much is gamma of z? Was gamma L times what? Gamma L has already a phase in there. All right, so this is going to be gamma L e to the minus j 2 beta z minus phi sub L. Okay, beta. How much is beta? So I need now to calculate this one. I have this and I have that from the problem. You see them there? Here. Phi sub, well, I call phi sub L, theta is minus 61 almost. Gamma magnitude was 0.76. All right? So I will write here 0.76 e to the minus j 61, say. So this is going to be 61 degrees. Okay, so practically I know, and this is 0.76. What I need to do is to find this number. So 2 beta z. How much is z? 15 centimeters. So you will have to do one of the two things. Either you have to convert beta in beta, you remember beta is 2 pi over lambda. Either you have to convert that in physical length, so it's going to be 1 over a physical unit of a length, or you will have to convert this in wavelengths. All right? Since I gave it to you in centimeters, I could have given it to you in wavelengths and say, I want this length to be half a wavelength. A lot of times we'll give it like that. So if I gave it to you as half a wavelength, how much is that? Okay? So practically, this one is going to be 360 plus 61, which makes it 421. And I know that the final result is going to be 0.76 e to the minus j 421, which is a 61 at the end. Okay? That's, yes.
Is 2 beta z always 360 impedance? Or just for this example?
360, no, this is for this example that makes lambda over 2.
Oh, okay.
Yes. Question? Any questions? Okay, the last 10 minutes. Let me see what else. This is the standing wave. I'll leave it for next time. Yeah, this is, but what I would like you to do is the transition today we had from the parallel plate waveguide to this was important for you to connect the things that we've learned with the things that we are learning now, and to see that there was a reason that we went to statics before we started this. From this point on, I want you to feel comfortable with these equations. All right, I have given you in the notes a lot of examples that you can do. And from this point on, we are going to be solving problems like this in class. We are going to solve them on Monday, on Tuesday, and on Wednesday, we are going to have a quiz. Only on the material, we started like after the break. Okay? So I'm going to give you a set of problems today to practically starting to practice with this stuff. Any questions, concerns? Okay, thank you. Hi.
I emailed you
Yes.
about the thing, and you said to meet you after class.
Yes, yes.
Yeah,
So tell me a little more, remind me.
It was about how I got a 90% on the individual homework, but I got like a 40% on the group, not homework, midterm.
Midterm,
Yeah,
and 40% of the group?
On the group one, and it really brought down my grade.
Yes, I understand. Okay, so here is what I plan to do. I plan to give a makeup assignment on Sunday. So yes, the second one. So I suggest you take it.
What was that?
I suggest you take it.
Okay. I took the first one.
Yes, so take the second one. If for some reason, by then, it's going to be the Sunday before the final. But if for some reason you don't feel comfortable, I may give you a third one.
Oh, okay. That'd be really nice.
Yes.
Thank you so much.
Sure. Okay.
Yes, sorry. So one protein is good? No.
Did we do what? Oh, yeah, for 100 megahertz, then I changed it, of course. I put something much bigger. I put 150, not a 15, all right? So I changed it in this, which equivalently would have been 150, yeah. I did that to simplify. Yeah, no. Yeah, I did that to simplify the, simpler, yeah. Right. that way is that. Otherwise, it would have been not 360, but it would have been 10 times smaller, 36, if it was only 15.
Okay.
Okay, yeah. Hello.
I was wondering if you were available to meet anytime on Thursday or Friday this week.
Thursday, I'm going, in fact, tonight I'm going out of town, and I will come on Friday night.
So
Do you have
Monday?
Monday? Yeah, absolutely. I'll be there all of next week.
Okay, great. Should I email you on what time?
Yeah, I'm in fact Monday. I have, if you come, right, I have office hours from 11 to 12. We can meet, and then we have class at 2, so we can meet at 12:30 in my office.
Okay.
And I will send you directions. Just send me an email so I can send you the directions.
Okay. Sounds good. Thank
Okay, sure.
you. Yeah, Jose. Or yeah.
Yes.
On the notes that I gave you, do you want me to put the score? I got the midterm paper.
The midterm is pretty good, the
Yeah,
score.
but,
But it's not included.
It's not in Canvas.
Oh, okay. I will then check it out and tell.
Okay.
Did you tell the TA? Because they are entering the grades.
Okay. Yeah.
So go and tell her. Yeah.
Yeah.
Okay, perfect.
Okay. All right. Thank you.
Okay.
Is it over there? Oh, there we go.
You can, what you can do with the group is if you are willing, you can upload it. Yeah, thank you. Or send everybody the copy, whatever is more convenient.
But when he sent an email for like tips, yeah. Did he like see
So on the last step that you just did, you said 2 beta z is 2 times 2 pi over lambda z.
Yes,
And then
because
the-
beta is 2 pi over lambda.
Right. So then,
Lambda over 2,
how did you get lambda?
lambda over 2, I gave it.
Oh, L is lambda over 2.
The z, I mean the distance, all right? At this point, z equals lambda over 2.
Oh, okay. So then
We are at the end of the line.
so the 2 cancels, lambda cancels.
Yes, and then the 2 pi remains.
2 pi remains. So that value is the
Is the phase of the reflection coefficient because of the z distance. That part, it's not that, it's that part of the phase. You remember that was this one. This comes here. Okay, it's this one.
So this equation is when you work with the characteristic impedance.
This is at the end of the line.
Oh,
Gamma
at the end
L.
of the load.
At the at the end of the line here, meaning at the load.
where the load
This is at the point z.
Oh,
and
so
then-
these are two different versions.
Yes,
of the same
exactly. This is,
parameter.
yes, it's the same. So, for example, what that means is that gamma at z equals 0 is gamma L. All right?
Oh,
It's
yeah.
gamma L.
Yeah, okay.
Yeah. So it's that one.
Okay, that makes sense. And so if you get a gamma value of 1, does that imply that all the wave is reflecting or?
Yes, if you get gamma equals 1, it means that the only thing that is going to happen is that gamma z is going to only have a phase. along the Z, but the magnet is going to be 1.
Okay.
So, right?
So like when we have that V plus
Yes,
wave, it's going to reflect with a phase change of 180.
exactly. It depends. So gamma L, it depends. If gamma L is 1, it's going to reflect with 360. If
okay,
gamma L is minus 1, it's going to reflect with 180.
Okay. So this just tells us how it reflects.
Yes.
This is not telling us that, oh, the whole wave got reflected.
Well, in reality, it did. All of your power
Oh,
got
yeah, it did.
reflected.
Okay, yeah. Because your
It's only the
magnitude is-
phase change.
okay.
So in one case, if you plot it as we do next time,
Yeah.
when in this case, it's going to look like this. In this case, it's going to look like this.
Because it's reflected
Yes.
at 180 phase change.
Yes.
Oh, okay, okay. And also, one question I had earlier in the lecture, you had given us the, when you solve for the V, when taking this, like when you got these equations,
Yes.
and you took the second derivative,
Yes.
and you said that that was similar to the wave equation.
Yes.
So both equations are giving us the same
Yes.
quantities.
Yes.
So which one do we use? Like
Beta and the one that with beta.
the one that you had here?
Yes. Because I'm going to give you beta. And I'm going to give you Z naught.
So what was the significance of?
To see that the Z naught can be calculated out of R, out of L and C for
which gave us
lossless.
this
Yes.
result. So
Because I may
okay.
give you L and C and say find Z naught.
Oh, okay.
I may not give you Z naught explicitly, but
Right.
I may give you the R and the L and C of the line.
Right. So that derivation helped us show that there's a relation between
Yes.
L and C
Exactly.
and beta, and how we
Yes.
can work interchangeably with
Yes.
that. Oh, okay. Okay. That.
And also if I give you L and C, not only you will find beta, you will find Z naught.
Right, because of.
Yes.
Yeah.
Of this is square root of L over C.
Ah, okay, okay. But this is only for a lossless transmission
Yes.
line.
And so far this one was lossless, obviously. Yeah. And I from this point on will only do lossless.
Lossless.
Yeah.
And one other final question: when
Yeah.
you drew this circuit schematic,
Yes.
this is specific to a parallel plate waveguide?
No,
or?
this is a generic for every two conductor line.
Okay, so any shape. Okay.
Yes, but the specific values for L and C
Yeah.
will vary depending on the cross section. Will
That
be
makes
different
sense.
for a parallel plate, different for a coaxial, different for a microstrip, and so forth.
Oh,
And they are given also in one of
Yeah.
the tables. Yeah.
Okay, so this is like the generic
Yeah, it's a
diagram,
generic
but
diagram.
these values will vary.
Yes.
Okay. Okay, great. Thank you so much.
All right. Thank you. Perfect. Okay, excellent. Yeah, thank you so much. Thank you.
Um,